Hello everyone, I'm coming to you from Central Ontario in Canada, and I'll be giving you a short overview of my upcoming paper, Adding Bone to a Bloomery Iron Smelt. Who am I? I've been a professional artisan blacksmith for over 35 years. I've had a special interest in living history, particularly from the Viking Age, including a long association with Parks Canada at L'Anse Meadows National Historic Site. Through L'Anse Meadows, I got interested in Bloomery iron smelting back in 2001. To date, I've done 92 individual Bloomery iron smelts. It's important to remember here that I'm an independent researcher and not attached to any institution. What was the spark for this experiment? Back about 2019, there was a fair amount of noise in the popular media about a concept that the Scandinavians during the Viking Age had been digging up the bones of their ancestors and adding these bones to their metalworking processes, theoretically in some attempt to improve the quality of the weapons. On some research, I found that this could be traced back to a paper written in 2004, Roll the Bones from Iron to Steel, by T. Gonsom. Now, I had some technical problems with some of the description of metalworking process contained in that paper. Through experimental archaeology, I decided to actually test what actually does happen when bone is added to an iron smelt. I had been involved in an initial test by Emma Harrison, then an honors student at the University of Aberdeen, during part of our Turf to Tools project in 2014. The furnace used then was based on a Pictish model post-Roman Age. Emma would add portions of bone totaling 5.2 kilograms to the end charges of a very large smelt. Emma would later take part of the top of the bloom and subject it to laboratory analysis, and the discovery was there was no noticeable effect. There was some change in the composition of slag during the very end sequence of the smelt, probably attributed to the calcium from the bone. Importantly, very few bone fragments were actually recovered. This experimental smelt was carried out on June 20th, 2020, here in Grey County. The intent was to test for the physical survival of bone. For this purpose, we established a clean base of sand over top of concrete slabs. The furnace was a proven design used dozens of times in earlier experiments. It is a short shaft type, 28 centimeters internal diameter, 66 centimeters tall, set up for slag tapping and bottom extraction. To ease extraction, the furnace is set on a stone plinth packed with charcoal fines. The walls are made of a mixture of high temperature clay, sand, and shredded dry horse manure. The rear is a heavy forged copper, 2 centimeters internal diameter, set at 22 degrees down, 5 centimeters proud of the interior. This gives us a stack height of about 50 centimeters and a base below the rear at about 20 centimeters. The smelt would use a fairly standard operating sequence. We would add a total of 25 kilograms of red oxide analog that was developed here. The main sequence charcoal consumption would be 6.7 minutes for each kilogram. The main sequence ore addition would be 7.9 minutes for each kilogram. The total ignited time for the furnace was approximately 5.5 hours. We would expect internal temperatures to exceed 1300 degrees Celsius. One first error in the experiment was there was no reference made of the time required for the final burn down after the last charge to the extraction of the bloom. Obviously, the bones selected would be critical to this experiment. I chose to use Canadian domestic types easily available locally. This included turkey as a substitute for a large poultry like goose, pork, and beef bones. Some of the bones retained the meat and were raw. Some had been previously cooked and used for meals, so I had the meat stripped away. Some had been boiled with all the marrow and meat removed. One experimental error was that none of the actual physical weights of the bones was recorded. How were the bones added to the furnace? The first set was placed in the base on top of the thin layer of ash and still burning charcoal from the preheated fire. These bones were immediately covered with large pieces of rough charcoal, the first ignition process of the furnace itself. This set of bones would be subjected to a total of over 330 minutes of high temperature. It was felt that this simulated a food offering at the beginning of a smelt. The expectation was that there may be some remains, primarily because the heat of the furnace travels upwards, not downwards. After some discussion, it was decided to change the original plan and make not 2, but 3 additions of bone. The second addition was made partway through the main smelting sequence. At this point, the furnace had been burning for 135 minutes. There had been 4 kilos of iron-rich tap slag added to promote formation of the slag bowl, plus 1 kilo of ore. You can see that the bones have been placed away from the rear side of the furnace. These bones would be subjected to approximately 200 minutes of high-temperature burning time. It was felt that this simulated a functional addition of bone in an attempt to modify the process of the smelt. Our expectation was that there would be no physical remains from this addition. Should be noted that a potential experimental error again is that this is a very small addition of bone if the expectation was to impact the smelt itself. The last addition of bone was made after all the ore had been added to the furnace. At this point, the body of the furnace had been burning for 305 minutes. There would be one final load of charcoal, 1.8 kilos, placed on top of this bone, and then the furnace would be allowed to burn down. You can see that the bones were placed centrally in the furnace. These bones would be subjected to a little bit over 30 minutes of full burning time. It was felt that this simulated garbage disposal from a group meal. The expectation again was that there would be few physical remains. Those familiar with iron smelting will notice the bright sparks seen in this photograph. This is an indication of the air blast eroding the top of the bloom, potentially the bloom sitting too high in the furnace. Careful examination of the resulting debris would be important to determining what bones may have survived. Of interest to any archaeologist watching this presentation will be the remains left after extraction itself. The first thing you see is that tap slag has been moved away from the furnace after it's been created, mainly to get it out of the working area. During extraction, hot debris can be expected to be pulled to either side for the safety of the workers. One of the first materials to be removed is the charcoal fines packing from underneath the slag bowl. Pieces of the slag bowl will be broken away to expose the bloom. Several of the base plinth stones had been removed to create a larger working space. It's not unusual to break away several pieces of the lower furnace wall. These may be partially baked into a rough ceramic. Sometimes pulling the bloom clear will also pull free the remaining slag bowl, which means large pieces of this may be found. A spray of fine ash, partially consumed charcoal, can be expected in a fan shape from the mouth of the furnace. The last remain from an iron smelt, beyond the body of the furnace itself, will be the bloom that was produced. These are not expected to be found at the iron smelting site, however. In this case, the bloom was a disappointing 2.6 kilograms, representing only a 10% yield. The cause for this was felt to be that the slag bowl itself had formed too high in the furnace. Back to the intent of this experiment, which was discovering any bone fragments remaining after the smelt. The process used was first to lay out the working field using a set of steel rods to map 30 centimeter squares. Each one of the squares was individually photographed and then examined for any remains. This was accomplished by first removing any larger pieces of furnace or slag. Then individually the fine debris was screened through the fingers. This allowed us to have a resolution down to about 5 millimeters. As individual fragments of bone were discovered, if possible they were photographed in place, their location was plotted against the overall grid, and then the individual bones were bagged. It should be noted that there was no attempt made to screen the debris beyond the 5mm hand sorting. What was recovered? First, there was a number of small fragments, quite shattered, of poultry leg bones. These were pulled clear with the charcoal fines. There was only one piece of poultry breastbone recovered. It was found with slag encasing its lower surface. There were a number of pieces of what appeared to be the larger beef bones recovered. These were found laying on top of the charcoal fines, all of which showed heavy burning. It should be noted that only a total of 15 fragments of bone were found. None could be clearly identified as being pork bones. What conclusions might be drawn from the recovered bones? First of all, the poultry leg bones were found within the charcoal fines. This suggests they were likely survivals from their placement in the base at the start of the experiment. All the poultry breastbone pieces were encased in meat and been placed in the furnace with the keel, the central rib, side upwards. This suggests that the piece recovered with slag on its bottom surface had actually survived its descent through the furnace from the last addition of bone. The beef bone pieces were only partially burned. Their location found on top of the charcoal fines, but within the ashes, suggests that they may have been part of the last addition of bone, but this is actually uncertain. Taken all together, this suggests that the best survival of bone may come either from a very last addition before burn down or from bones placed in the base of the furnace, suggesting a possible ritual use. What could come next? One investigation could be into the potential cooling effect of bone encased in meat when placed at the base of an operating furnace. What is the potential impact of larger amounts of bone, especially if added with each of the individual ore charges through the main sequence of a smelt? Small amounts of phosphorus alloyed to iron are known to harden the final metal. Is it possible that larger amounts of bone added to an iron smelt would actually change the potential phosphorus content? This experiment would require institutional support for the lab work required. I'd like to acknowledge the contribution of Neil Peterson and Ray Cogswell in undertaking the actual physical smelt part of this experiment. Neil has also become a trusted advisor and major smelt partner over the last 15 years. Additionally, members of the Dark Ages Recreation Company have assisted in many smelts over the last 2 decades.